So the demand for advancements in indoor comfort has increased over the years, and such improvements have led to an increase in energy usage in space heating and cooling. Heating and cooling alone, on average, accounts for 24% of a building or household's energy consumption. As such, there has been a need for improvements in the efficiency of space heating and cooling technologies. One such method would be to reduce the energy needed to reach desired temperatures, and to accomplish such a task, the room would need to be capable of passively maintaining temperatures near desired conditions without the aid of heating and cooling systems. This can be accomplished using phase change materials. Phase change materials are substances that absorb or release large amounts of energy during a phase change, such as from solid to liquid, it would absorb a large amount of heat. What can be done is to take advantage of this nature by using a PCM that changes phase around room temperature and embedding building walls with it. Through this, the walls will passively heat the room when it's too cold, and the PCMs release energy in the form of heat, or passively cool a room down when it's too hot, and the PCM melts and absorbs large amounts of energy as heat. Such a technology would potentially reduce the cost of space heating and cooling. First, I'll talk a bit about the project from last semester and how it ties into this new project. In the prior semester, the main project I was working on was thermal energy storage using cementitious materials. The project was to design a thermal energy storage system that was capable of operating around 400 degrees Celsius, maintain 90% round trip efficiency, and cost less than $25 per kilowatt hour. For the design, the plan was to have two plenum chambers, one on top of the concrete and one below the concrete, as seen in the graph or the figure. And a heat transfer fluid would pass through these chambers and transfer heat to the concrete via thermosiphons that are running through the concrete block. This project is still continuing with the core team. In this new project, we are testing the effects of integrating phase change materials into concrete to act as a passive heating and cooling mechanism. While this current project focuses on using PCM concrete in room temperature settings, the potential for this study is implementing PCM in the thermal energy storage system concrete, as a PCM with a phase change temperature around a power plant's operating temperature would allow this storage system to absorb much more thermal energy per unit volume and increase storage capacity. For the literature review, we first look at PCMs that we possessed and whether or not they had a phase change around room temperature. And then we looked at various papers by other institutions to research methods for experimentation and implementing PCMs into concrete. The best method was by encapsulating the PCMs within porous aggregates that would be inside the concrete. Other methods, for example, simply mixing the PCM into the concrete mixture, led to cracking within the concrete after the PCM changed phase. We then looked at patents that may be similar to our project. However, the patents we found were all abandoned or expired, and other patents that were different enough in design allowed us to proceed. We narrowed down two main encapsulation methods for injecting PCM into the aggregates. We first have the soaking method. For this method, you submerge the dry aggregates in a container filled with melted PCM for several hours in an oven to keep the PCM in a liquid state. And you take weight measurements over time to determine how much PCM was absorbed by the aggregate. The second method is vacuum impregnation, which is similar to soaking, except we have the aggregates and PCM in a vacuum sealed chamber to remove any air trapped in the aggregates and allow more PCM to be soaked. Vacuum impregnation has noticeably better results than direct impregnation as porosity increases. So for example, an aggregate with porosity below 30% will see similar amounts of absorption between both methods, whereas after 30%, the vacuum impregnation method performs substantially better. Finally, we researched coating methods for the aggregate embedded in the PCM. Since in liquid state, the PCM will leak out. The most prominent coating methods included immersing the PCM in the aggregate into epoxy, and adding graphite as 15% by weight to the epoxy showed a noticeable increase in thermal conductivity. And another benefit of epoxy coating is that it increases the PCM's resistance to changing shape when the concrete experiences any strain. For the experiments, we performed tests on two types of aggregates, 3/4 inch norlite and 3/8 inch norlite. Norlite is a type of expanded shale aggregate. For the PCM, we had calcium chloride hexahydrate, which possessed a phase change temperature at 26 degrees Celsius or around 79 degrees Fahrenheit, which is fairly close to room temperature. For the initial tests, we wanted to run through them using water at first instead of the PCM to make sure we properly executed the procedure and not to waste the PCM and aggregates we had before we were sure about the full experimental procedure. We tested both encapsulation methods of soaking and vacuum impregnation using water to determine the method we would use in the final experiment with PCM. And here are two images of the vacuum method. So here's the vacuum, and inside this chamber, which is vacuum sealed, on the left, we have the 3/4 inch norlite aggregate, and on the right, we have the 3/8 inch norlite aggregate. They would be inside this chamber for about 3 hours. After 3 hours, all the air inside the aggregates that were trapped have been removed. And at this point, the water was inserted into the chamber through this tube. And then after an hour of soaking, the rocks are then removed and their weights are taken. So these are the final results of these experiments. So the first test we ran was for the soaking method for the 3/4 inch norlite and 3/8 inch norlite aggregate shown above. And the measurements resulted in the aggregates having an absorption around 22%, which means it was able to absorb 22% of its weight worth of water. And then the second test was using the vacuum method, which also ended up with around 22% absorption, which matches the results from other papers we read saying that when the absorption is beneath 30%, you will see both methods have similar absorption percentages. And then finally, we ran an extra test, seeing a method where after we have finished with the absorption, after we have finished with the vacuum method, we let air into the chamber for 30 minutes to push water further into the aggregate. However, this resulted in only a 1% increase in absorption, so it was not very different. I performed a cost analysis of our concrete PCM aggregate mixture to find the space heating and cooling reduction. For this, I estimated PCM performance and cost reductions using other reports and studies, as we were unable to perform our own tests due to the closure of the laboratories in the campus. From the mixture, we theorized certain ratios for a concrete block with aggregate and PCM inside and came to a cost of $22.44 per cubic foot. The household I looked at had a floor area of 2,600 feet squared and a wall area of about 1,500 feet squared. It's an average sized house. According to the studies I analyzed, we would expect an average space heating and cooling energy reduction of about 50% with our specific PCM concrete design. This would lead to an average of about 20% savings on electricity bills. And using a study by the US Department of Energy, I was also able to calculate the payback period, which varied greatly depending on the city heating and cooling electricity prices. And this table shows the different payback period values. So cities like Atlanta that had low costs for electricity for cooling had the longest payback period, but Phoenix, Arizona, that had the largest costs associated with heating and cooling had the shortest payback period. With the cost of analysis reports, it can be further seen how porosity affects the performance of the PCM concrete. One of the reports had divided their analysis based on the percent of PCM by weight present in the mixture and showed this logarithmic trend that we see in the graph. At low porosities, increasing the PCM content substantially improves the savings. However, as we approach 20% and 30%, the savings decrease. And typically you will see no more than 30% because after this point, the cost of incorporating more PCM starts to outweigh the savings. So unfortunately, due to COVID, lab access was cut off when we were ready to begin experimentation with the phase change materials. And while we should expect similar results, we still needed to test the coating of the aggregates with PCM inside. We also still need to test the compressive strength of concrete with the PCM aggregate inside to ensure that the mixture is capable of taking the strain caused by forces on the concrete in a typical setting. We also need to see how we can improve performance by increasing the amount of PCM we use, by potentially increasing the amount of aggregate in the mixture, or by using a higher porosity aggregate. And at this point, I will take questions. Thank you.
Thank you, Larry. Questions for Larry? As before, you can ask the question directly or send it through chat if you wish. Questions for Larry?
I have one, Rudy.
Yes, Cheryl, please.
Has there been any work yet on the effects of the porous material within the concrete in terms of its stability over time? I'm just wondering what kind of chemistry is going on in the walls.
Good question.
As in like how it's like over time as it goes through multiple thermal cycles, whether it can sustain it. Well, you'll really only see huge like effects at really high temperatures, and this is something that will come into play when we're attempting to integrate the PCM into our power plant level concrete. But for room temperature, you don't really see many issues appear over years. I didn't see any reports that specifically were about seeing the effects of this over years, because not many tests have been done that spanned over multiple years.
Thank you.
Larry, I have a question. Your data on Phoenix was most favorable. So any insights into that?
Well, that was from a report done by the U.S. Department of Energy. They looked at those specific states, and in their specific case, they tested multiple phase change materials, and they tested multiple temperatures in which those materials would change phase, and seeing different heat of change, trying to remember the word, specific heats of the phase change materials. And with that, they were able to also analyze the specific cost of electricity at different times of the day, different months. And then another report I looked at specific cities every month of the year, the kind of cost reduction you'd see from the PCMs. So obviously, the more southern states, they experience higher temperatures, and those will see the most favorable performances. But what could also be noted is that on the opposite spectrum, where those studies that you saw, none of them were very north, but the closer the temperature was to the phase change material temperature, the higher the cost savings was. So that's something.
Okay, good. Well, if you don't, can you unshare yourself, Larry? All right.
I believe I've stopped sharing screen.
Good. So we've come to the break, and although we have kind of overshot the runway a little bit, we still have time for the break. And also time for you guys to fill out the evaluation forms, either through Google form or through the hard copy that was mailed to you. So choose either option. The Google form is frankly far easier to kind of navigate, actually get it done right away. So are there any other general questions you want to pose to the students? Anybody? So,
Rudy, it's Al.
Al, okay, go ahead, Al.
When a couple presentations back, when Nick and Josh were talking, I'm not sure where it was, but somewhere on the line, my internet kept cutting out, and I didn't hear everything. So if this is a repetitive question, I apologize, but I believe early in Nick's part of the presentation, he said something about restricting power flow up through the subs. Was that a condition that was placed by the state, by PPL, or your study team? Because obviously the technology exists to let that happen, although modifications to the feeders are clearly necessary at some expense.
So I can jump in and answer that. That is kind of a restriction that was placed by the fact that we were using hosting capacity as the basis of our analysis. In order to fall within the realm of hosting capacity, there cannot be any modifications or upgrades made to the existing equipment. So like we had mentioned towards the end of our presentation in future work, that would definitely be something that could be considered in a cost-benefit analysis, future work of whether that expense would be worth it. But that was, it was not included in our project scope because that would be outside the definition of pure hosting capacity.
Oh, okay, thanks, Nick. Good point. One other question I had during your presentation, and either you or Josh might be able to answer it. When you're talking about these areas that have the highest capacity and also it's obvious the higher populations, obviously if you put it on roofs, I don't think most places have too many restrictions on that, but if you had to put it on vacant land, do these municipalities have any zoning restrictions or building restrictions about such use of open land?
Yeah, that was one piece that we looked into when we were trying to get the land cost, because we had to find industrial property. I forget exactly how they define it, but it had to be defined as something that was industrial to meet these specific type of restrictions. That was just easier for us when we looked into it. So as long as it fell into the category of industrial, it then already had all the municipal I would say approvals, whereas a residential, if it was then vacant, it would then it'd have to go through a few extra steps converting the land type.
Okay, thanks. Yeah, that kind of adds a little clarity to it, because like cities like Allentown and Harrisburg, for instance, probably have very little open land within their communities that are zoned industrial. So you'd really have to take it outside of those into the more suburban areas, most likely.
Jim Gallagher. Similar comment on that presentation, was just to find a way to incorporate community acceptance into the analysis. So you don't end up, putting solar farms where it might be cheapest, but people don't want them. And I'm not exactly sure how to do that, but I think that would be a really beneficial added feature.
Yeah, absolutely. Thank you. Yeah, we appreciate that.
And if I'm not mistaken, Josh, the community solar bill, the way it's shaping up, and I don't know what the status is, it kind of has something for everybody, where investment, different income levels is very favorable.
Yeah, it has a very nice compensation marked into the bill already. So it primarily outlines just the person's income, but how it then is pushed, I believe, is then based on the developers. Once it's approved, developers will then take on those projects, and then I guess their marketing teams will be the ones to go forth and convince everybody that it's great.
Yeah. Any other question for anybody? So hearing none, I thought, why didn't you, if you're still working on the evaluation form, please go ahead and complete it. It's a great way to get feedback because I kind of, their job as they go into the outside world is getting people to buy their presentation. And so they need to cover a lot of territory just as a way of how much time the students have spent, COVID or no COVID. I think it averages almost anywhere from 600 to 1,000 hours over the 2 semesters. So they've done a lot of work, hit some bumps on the road, many bumps on the road, dead ends sometimes. And so it's kind of a culmination of something that they've experienced in real life. So hopefully it was a good experience for the students. And somebody has his hand raised there. Oh.
I was waving at the neighbors.
Oh, okay, sorry. That's good. That's another part of this virtual learning is all sorts of interesting things. Let's see, on the chat, if you haven't received your evaluation form, hey, Susan, send a note to Susan and she can at least send that over to you, but it was sent in the package to all the, are there people who have these evaluation forms or can get them, or? There was one in the chat that requested it.
Hey, Rudy, this is Dan Chapley.
Yes.
Just a quick question. How do you want us to send these forms back? Because I tried opening up that form in Google Docs and it really doesn't seem like it's a fill in the form type of a thing that you could do. I mean, I have it filled out on paper, but is there a way that you could, that you know of, that we send it back to you, or do we just scan it in and send it back? How do you want to have it sent back?
All of the above. Google Forms allows you to fill it electronically and it does the rest. So when you say you can't do it, there's a...
Well, when I have the document from Susan, how do you open it up? Because I opened it up, downloaded it, and it became a document, but you can't fill it in.
You shouldn't have to download it. You should just click on the link and it'll take you right to the Google document. And then all the buttons are there. It's the exact same form that you have on paper. It's just nicely more laid out, and there's spaces for comments for you to write in for each team member that spoke.
Okay, I'll give that a try. Thank you.
Yeah, it's nothing you have to download.
Okay. Yeah, the Google form is probably the most convenient to work with. All right, so why don't we take a break before the next meeting? This will be an advisory council meeting. And I'll leave the connections open so you don't lose it, or you can take a bio break or get a snack, or if you want to get a glass of wine or a beer, go for it. All right. Hearing no more questions, the students, you guys are excused. Thank you again for participating.
Thank you to all of our visitors. Really appreciate your participation.
Thank you.
Thank you, everyone.
Thank you.
And we will have class next week, same time.
Rudy, how long did you say the break is going to be?
We will convene, we'll start up in another 19 minutes.
Okay, sounds good.
And for those of you still here, I did double check it. When you get to the Google form, you click on the link and then you fill your name in and then your email address. And then underneath that, there's a next button. You click next and that will take you to all the students' sections. It's all broken out by each student that spoke.
Susan, can you reset that?
Yeah, I'm sending it to you right now.
Thank you.
I just wanted to get that in there before I miss
Thank
everything.
you.